Lecture 15, Part 2, and we will go through our first search strategy that most of you should know already, called Breadth First Search, or BFS, and we're going to just talk about it formally in the terminology that we use for general search problems. So the first thing we're going to talk about is the frontier. So as I said, we only need to keep track of the frontier, so we're going to use Q, which basically is a first in, first out structure to keep track of the frontier for BFS. So basically, we remove from the front and we add to the back. So I think we need an example to explain what this is. So I will talk about the maze example, which is actually what you do in P5. And let's get a maze, a very simple one. And suppose we want to start from the initial state, which is labeled 1 here, and we want to search to solve the maze. Then what we do is we keep track of Q. Let's see, start from 1. And what we do each time is we DQ from the front and enqueue to the back. So we DQ the first state, and here we're expanding the first state, and we're going to put the successors at the back of the queue. So the successor of 1 is, say, 2 and 3. So I enqueue 2 and 3 at the back. So again, we DQ from the front of the queue. So this is our queue. And then we enqueue at the back. We put the successor, so we basically expand the state 1 and get the successors and put it at the back of the queue. So that's the first step, and then we keep doing the same thing now. So DQ2, which is at the front of the queue, and then enqueue the successors. What are the successors? I can go back to 1, but when I was already there, so I'm not going to add it again. Here we only have 1 successor, so enqueue 4 at the end. And then keep doing this, DQ3 and enqueue the successor. Again, we're not going to include 1, and we're going to put 5 at the end. So we can continue this process, 4 and say 6 and 5, and 7. So now if we DQ 6, there are no successors because we're at the dead end, so we just don't enqueue anything. And now we just DQ the next one, which is 7, and putting 8 here, 9, 10, and so on. So I will not continue this process. If you want to draw the tree, if you want to draw the search tree, then what we're doing is expand 1 level at a time. So 1 get expanded to 2 and 3. 2 get expanded to 4, and at the same time 3 gets expanded to 5. And we're not going to continue searching 4 before we search 5, so we're going to do them at the same time basically, and continue here to 6, 5 to 7, and then we reach a dead end here. So we are going to continue here to 8 to 9 and so on. So if we want to draw the search tree, it looks something like this. So the next slide is just a summary of what happened, a bit more formally, but it's the same idea. It's just again how to actually implement this. So I'll skip it in the lecture. And now we are interested in whether the search algorithm works. It turns out they do. So BFS is a simple algorithm, but they work. So it is complete. So it always finds at least one solution, and it turns out it is also optimal. I'll talk about this in the next lecture, why they're optimal. And another measure that we're interested in, the complexity. So first, the time complexity. So basically, what's the worst case number of states that we need to search? So if we look at the tree, suppose the goal is here, so the depth is d. Maybe we have more, so the total depth is d. However, if we use BFS, then we're going to search one level at a time. So at the beginning, it's just 1, and then we are searching these 2, and then we're searching these 4, so 2 to the power 3, and then 2 to the power 4. We search all of them. And if the goal is here, then we need to search through all of these 7 until we reach this. So we actually need to search all of these nodes. And the way to count them is just b. So these two, b plus b squared. So suppose b is 2, then it's b squared until b to the power d. We should probably include 1 plus at the beginning, but adding 1 doesn't really matter. So if you are familiar with the big O notation, which you don't need to, it will not be a part of this homework and the midterm. But if you are, then it's just big O of b to the power d. So what it means is all of these other terms are kind of small compared to this. So we only care about the term with the largest exponent, and we usually measure the complexity by just worrying about the largest term, and also we don't care about the constants in front. So that's big O of b to the power d, and the space complexity is how many states we need to keep track in the frontier. And as you can see, in the last step, we need to keep track of all of these 8 in the frontier at the same time. So that's basically our search tree. So we need to keep track of 2 to the power d here, which in general is b to the power d. So the space complexity is b to the power d, and again, it's big O of b to the power d, so it's kind of large. So one of the extensions, the natural extension of BFS, is we can search from the initial state and the goal state at the same time. So it seems it's kind of halving the time. Indeed, it is. So basically, if you have a maze, then you can search from here and also search from here, and somehow they will meet in the middle. So we don't need to search from like everything. So that diagram is confusing, but we hopefully will just do like around half of the work. So it turns out that the time and space complexity is basically the same as BFS, except for the depth is halved.